Welcome, high school teachers. So in our first module, we had a look at classical curves, going back to the ancient Greeks up to the 17th century. Today we want to move to the 20th century, very important development in the history of curves that was remarkably the work of two French engineers working for car companies. So to set the stage, let's have a look at where things were in terms of describing curves in the first part of the 20th century. We basically had two different approaches to curves in the plane. One was an algebraic approach, where we thought of a curve in terms of an equation involving x and y that specifies the points on the curve. So here, for example, is the example that we call the folium of Descartes. It's a cubic curve, as we can see, because it's a degree 3 polynomial, and it has this rough shape. Now, suppose you wanted to actually graph this curve from the equation. That might not be so simple because it's hard to find points that are exactly satisfying this equation without a little bit of thought. So there's another way of thinking about such a curve, which is a parametric form. And it's going to play an important role in the story today, the idea of going to a parametric view of a curve. So in this particular case, there is also a parametric formula for this curve. So it has also a parametric equation, and that is minus 3t over 1 plus t cubed and minus 3t squared over 1 plus t cubed. So for any value of t, if you plug t into these two expressions, you will get a point. And then you can check that this point actually lies on this curve. So that's an algebraic identity that says that this thing cubed plus this thing cubed plus 3 times their product always equals 0. Now this parametric equation is very useful for actually plotting the points because you just plug in a value of t and you get a point. T equals 0. Well, that's easy to see. It's right there. If t equals half, somewhere around there. T equals 2 is here. T equals minus 2 is maybe somewhere here. T equals minus a half is somewhere there. So there's t equals 0. This is t equals a half. That's t equals 2. This is t equals minus a half. This is t equals minus 2, for example. And you could easily cook up more points on the curve. All right, so we have these two different ways of thinking about a curve, an algebraic equation or as a parametric equation. And let me remind you about a very simple form of the parametric equation that we talked about in the previous module in this course. That was the idea of what happens if you have a line through 2 points. Suppose we have a line through 2 points. Say A1 and A2. And suppose that the vectors of these 2 points are A1 and A2. These are the vectors from the origin to these 2 points. Then this vector here is the vector which is the difference, A2 minus A1. And then this line L can be described parametrically as A1 plus lambda times A2 minus A1. All right, so I'm recalling this parametric form for the equation of a line, where you start with a point on the actual line with coefficient vector A1, and then you add to that any multiple lambda of the vector that's in the direction of the line, joining these 2 points. And we can rewrite this, if we like, as the expression 1 minus lambda A1 plus lambda A2. And we recognize our favorite convex combination. These two numbers always add up to 1. And in a special case, when the parameter is between 0 and 1, then we're just getting the line segment A1, A2. We get the line segment between A1 and A2. However, if lambda is bigger than 1 or less than 0, then we're getting points outside this line segment. Okay, so this is the key point that these two French engineers used to completely revolutionize the story of curves in the 20th century and provided a huge new way of thinking for engineers, for architects, for designers, for computer scientists interested in curves. In our modern, highly technological industrial world, curves come in many different shapes and sizes. And we're going far beyond the rich but somewhat limited family of classical curves that were studied in ancient history up to the 18th and 19th centuries. So we have curves appearing in many different ways in the modern world in terms of designs of ships, cars, planes, trains, in terms of simple household appliances like toasters, design like chairs or buildings, waves, perfume bottles, mobile phones. Everywhere we look in the modern world, there are curves, and these curves have to be designed by someone and have to be constructed and created by engineers and builders and so on. So in the modern world, it became clear that we needed a more general and flexible way of thinking about curves that goes beyond the classical theory. And remarkably, it was two French engineers who came up with this beautiful and powerful way of thinking about curves relatively recently. So they were Paul de Casteljau and Pierre Bezier. And they worked for competing French automobile companies. Paul worked for Citroën and Pierre worked for Renault. And in the period about 1959 to 1962, they independently discovered this new way of thinking about curves that gives a way of specifying and controlling shapes of arbitrary curves. For example, maybe you're interested in a car, okay? And perhaps you've painstakingly decided that this is the shape or the outline of the car that you want. So how are you going to express this curve mathematically? It's for sure not going to be a classical curve. It's not an ellipse or a cycloid or a cissoid or anything like that. It's something that you created with the help of your designers and your engineers. But you still want to be able to capture this curve mathematically in such a way that you can transfer it to somebody else. You can send the information of that curve to somebody else, maybe not necessarily by sending them a photo. You want it to be easily modified so that if somebody wants to move this just a little bit down, that they can modify it without having to start from scratch. And preferably, if you're mathematically inclined, you'd like to have a way of doing this which is mathematically elegant. And of course, simple is good. So remarkably, Paul and Pierre discovered such a way of understanding curves, which really was a major revolution in the history of algebraic geometry and the study of curves, coming from engineers. So let's see what they did. Okay, so let's explain the basic idea of these de Casteljau Bezier curves. And by the way, they're usually called Bezier curves these days, but it's certain that Paul de Casteljau deserves just as much credit as Pierre Bezier. So perhaps I'll generally call them de Casteljau Bezier curves to give de Casteljau his due. Okay, so here's a very simple situation. We have 3 points. We're going to call them P0, P1, P2, and we're going to connect them with line segments. And what we're going to do is we're going to think about this very simple parametric motion of a point going from P0 to P1 determined by a parameter. We called the parameter lambda previously. I'm going to change that to t, t being more like time. We'll think of t as being like something time progressing. Okay, so we're going to put a point here. Let's put it there, and we'll call that point, say, Q0. So this is a point on the segment between P0 and P1. And so it can be described in terms of its coordinates as Q0 equals 1 minus t P0 plus t P1. So we're using the vector notation here, even though we've got points, but you should think of these things as the coordinate vectors of the points in question. So 1 minus t P0 plus t P1, as t goes from 0 to 1, this point will move from first P0 when t is 0, all the way up to P1 when t is 1. Okay, it's going to be steadily moving along here as t ticks from 0 to 1. Now at the same time, we're going to have another point moving from P1 to P2 by the same kind of procedure, and we'll put it here, and we're going to call that Q1. So Q1 is 1 minus t P1 plus t P2. Now notice that the t value for Q1 is the same as the t value for Q0. So if Q0 is 1/3 of the way along here, then Q1 will be 1/3 along there. When Q0 is 1/2 way along, when t is 1/2, then Q1 is going to be 1/2 the way along this segment. So they're moving sort of simultaneously, synchronized, so the movement's sort of like this. Okay. Q0 starts here, Q1 starts here, at time t equals 0. When the clock starts ticking, they're moving like this, and at t equals 1, Q0 is up here and Q1 is there. All right, so we have now this line segment joining Q0 and Q1. And now the interesting idea is to consider a third point, which is on this segment Q0, Q1, which is proportionally the same amount between Q0 and Q1 as Q0 is from P0 to P1. In other words, we're going to define this new point. Let's call it PQR, R0. By the same kind of formula, 1 minus t, but Q0 is the first point, plus t Q1 is the second one. So while Q0 is going from P0 to P1, Q1 is going from P1 to P2, this R0 point is at the same time venturing from Q0 to Q1 along this moving segment. And now what happens to R0 as we watch the whole movie progress? Well, we get a curve. Like this. So the path of R0 gives us a Bezier curve, or a Casteljau Bezier curve. The path, or locus, of our point R0 gives a Casteljau Bezier curve. And that's the curve that we're interested in. So what kind of a curve are we getting here for this Bezier curve? Well, it turns out that it's a conic section. In fact, it turns out that it's always a parabola, or a part of a parabola. And these 3 points, P0, P1, and P2, are called the control points. So they determine the shape of the Bezier curve in the following way. So P0 and P2 are actually points on the curve, namely the start and the end of this little arc. P1, of course, is not actually on the curve, but it controls the shape of the curve in a very important way. Namely, the tangent to the curve at P0, the direction in which things are going, is towards P1. And similarly, the tangent to the curve at P2 is towards P1 from P2. So P1 controls the tangent directions. And you can think about this as some kind of a story where we are starting here and sort of attracted towards the P1, so the particle's moving to P1. And then as time ticks on, it becomes more and more attracted to P2. The attraction of P0 diminishes, the attraction of P1 eventually diminishes, and eventually it's attracted to P2. So the actual formulas are very simple, very elegant, and kind of uniform, and this gives us a quadratic de Casteljau Bezier curve. And a very nice way of controlling the shape of a simple parabola. But things get more interesting when we go to the next degree up, to the cubic de Casteljau Bezier curves. All right, so we're going to go up in degree 1, and we're going to do that by having 4 control points instead of 3. All right, so our starting point is 4 points, P0, P1, P2, and P3. And these determine 3 line segments. I'm going to play the same kind of game that we were playing in the quadratic case. We're going to create a point, Q0, which is moving along this line segment. We're going to create a point Q1, which is moving along this line segment, and a point Q2, which is moving along this line segment. And those are created just by this well-known technique of convex linear combinations, taking a weighted sum of P0 and P1 to get Q0, the same weighted sum of P1 and P2 to get Q1, and the same weighted sum of P2 and P3 to get Q2. So as t, this variable or parameter, goes from 0 to 1, Q0 is moving like this, Q1 is moving like this, and at the same time Q2 is moving like that. All right, so what else did we do? Well, we joined Q0 and Q1, and on this segment we last time created another point, R0, which is the same kind of weighted combination of Q0 and Q1, namely 1 minus TQ0 plus TQ1. So as these points are moving, this line segment is moving, but R0 is still taking a walk along this line segment, starting at this end when t equals 0, and ending at the other end when t equals 1. But now, for symmetry, we also need to introduce a second R point, one that's on the segment from Q1 to Q2. So there's 1 minus TQ1 plus TQ2. That's the point R1, which is moving on this segment as it's moving. All right, so now we have to go one step further from what we did last time, introduce another point. And we're going to do that by traversing the segment between the R points. There's another kind of segment. And on that segment, we're going to put a new point, which is also, say, a third of the way along. And let's call that S0. All right. So the new point that we're introducing, S0, is 1 minus T R0 plus T R1. So we have all these points moving from one end of the segment to another. And the point that we're really interested in is this S0 point. And its trajectory gives us cubic the Casteljau Bezier curve, which might be something like this. So the cubic the Casteljau Bezier curve is the path or locus of our point S0. And it's generally a cubic curve. Given by a degree 3 polynomial in x and y. And these 4 points, P0, P1, P2, and P3, are called the control points of that cubic curve. Let's give that curve a name. Let's call it, say, C. All right. Then these points P0, P1, P2, and P3 are the control points of C. Now they have a bit of a different nature. So P0 and P3 are the endpoints. They're actually on the cubic, whereas P1 and P2 are more giving directions for the direction of the curve. So they're specifying the tangent direction as we emanate from P0 and the tangent direction as we emanate from P2. And so they're a little bit more indirectly controlling the curve, but nevertheless, it's not too hard to maneuver those points around, and then the curve will move around, and with a bit of experience, you can make this cubic go where you want it to go. So in practice, you could go to higher dimensions. You could add more control points and get higher degree de Casteljau Bezier curves. But in fact, in practice, most of the time, quadratic and cubic ones are the ones that are mainly used. Because they're simple to operate, you only need 3 or possibly 4 control points. So what happens if you have some more complicated curve? Something like this. And you want to describe that using the Casteljau Bezier idea. What you do is you break it up. So you get some story maybe like this. All right, so this part of it will deal with this part of the curve. All right, so you have 4 control points giving you that sort of cubical arc. And then you think of maybe another, breaking it up at this point as well. Okay? So there's another little cubic arc. And as long as this tangent and this tangent line up, so they're actually parallel, then this curve and this curve will smoothly match, and it will have a very nice smooth appearance. And so you can carry on doing that, breaking the curve up into suitable pieces, creating little cubical Bezier curves, and then putting them together to get the entire curve. That's the basic strategy for describing all kinds of interesting shapes, including fonts. Okay, so like TrueType or PS fonts, all these different fonts that are out there. If you want to describe a font, this is the way it's done, by figuring out where the control points are, breaking the thing up into little segments, and then you have a nice, easily specified, very compact way of representing the shapes. All right, so in our next module, we're going to have a look at actually playing around with this. So it's good to get some hands-on experience to see how the control points control the shape of the curve. And to do that, we're going to play around with GeoGebra. So I'm going to give you a little bit of an introduction to GeoGebra, and then we're going to use GeoGebra to construct some Bezier curves and manipulate them.